At a factory, a box is moved by the cables attached to a beam in the position shown. The box is not moving. What is the tension in the left, right, and vertical cables? All right, so I'm looking for tensions. If I'm looking for tensions, thing is, a tension doesn't have its own formula. It's part of other formulas. So in other words, it's about free body diagrams. So if I want to find tensions, I've got to find free body diagrams. And when I look at this, I see two bodies. One of them is the knot that's holding the three tensions together, or three cables, and the other one is right there where the knot connects to the top of the box. Okay, so what's my strategy? I'm going to draw a free body diagram with the knot, and I'm going to draw a free body diagram with all the forces acting on the box. So here's my dot for the box. It's got tension going up, and then it's got mg going down. That's all I've got on the box. No surface, no friction, no acceleration, nothing interesting. Just a rope and gravity. So that's easy enough. Now for the knot, I've got TV. I'm going to call it TV, V for vertical, going down to the box. And then I've got this 20-degree angle and tension on the left, 35-degree angle, tension on the right. And you can see my dotted line just to kind of give me a reference point. That's not a force, it's just there to give me some kind of reference to my angles. So at this point, I have kind of an interesting problem. I need to break this up into horizontal and vertical forces, and TL and TR at angles. Trig. I'm going to use trig, and I'm going to use trig and break the TL and TR up into a triangle, make it look like a triangle with horizontal and vertical components, and that'll get rid of the TL, the angled TL and the angled TR. Okay, so College Board rules. This is the first free body diagram. And if you have lines, forces that are at angles, you have to draw a second free body diagram. And on the second free body diagram, you have to show the components. So the first one, it's just to show where the forces are. And the second one is really the one where you use everything. So here's my dot, here's my knot, sorry. And here's the second one. TV going down from the knot, TL, TR. Okay, it looks like the other one. And now here's the difference. I got to put components. So the adjacent side, adjacent is cosine function, so TL cosine 20. And then the opposite side goes up. Remember, when you're adding vectors, you connect them tip to tail, and they start at the same place and they end at the same place. So going up, that's opposite of the angle. That's going to be the sine function, TL sine 20. Now for the side on the right, I'll go adjacent side, adjacent to the angle. So that's going to be the cosine function, TR cosine 35. Connect the vector tip to tail so it ends up at the top where TR is. And that'll be the sine function because that's opposite of 35 and sine is opposite of our hypotenuse. So TR sine 35. So this is really the two equation or the two free body diagrams that I'm looking at. I'm not going to be looking at the other one, although I've got to show it. So these are the two that I'm really going to use. All right, now that I've got these components, the TR and TL that are an angle and the 35 and the 20 degrees, they go away. I don't need to consider them at all. They're done. All I have are these vectors to look at. So I'm looking for the tension. So TV and the T in the box, those are actually the same cable. So they're actually the same tension. That could be easily just labeled mg going down and TV going up. So I'm going to sum up the forces on the box. Sum up the forces in the y direction is equal to 0, which is equal to TV minus mg. Remember, I just told you they're the same. So therefore, TV is equal to mg, and they give me the mass of the box. So that's great. I actually just solved one of the questions I'm looking for. The vertical tension in the cable was 431 newtons. Well, that was easy. Now, there is no summation in the x direction because there are no forces in the x direction. So let's move on. Let's look at the free body diagram for the knot. I'm going to do the same thing, sum up the forces, because that's where the tension lies are in the summations. Okay, this is going to be crazy algebra with a lot of substitutions. So let's start with this. In the x direction. Now, if you want to, you can pause anytime and try this and then see what my answer is. So here's my summation in the x direction. Pause now if you want. Sum of the forces in the x direction is equal to 0 because it's not accelerating. And that's all the forces going to the right minus all the forces going to the left. So I've got TR cosine 35 minus TL cosine 35. Notice this does not include the TR sine and the TL sine because those aren't horizontal. So these are just the horizontal forces. Okay, this means that 0 is equal to TR cosine 35 minus TL cosine 20. Sum of the forces in the y direction, I should have let you pause and do that one. Sum of the forces in the y direction is equal to TR sine 35 plus TL sine 20 minus TV. So there are three vectors that are in the vertical direction, and this is how they add up. All the ones pointing up minus the one pointing down. All right, so that means that 0 is equal to TR sine 35 plus TL sine 20 minus TV. Now I'm going to isolate TV because I already know TV. It's equal to mg, or 431 newtons. I found it out earlier, remember? Okay, here's the crazy part. I've got to start reducing the variables down and eliminating them. So I got to start rewriting equations in terms of other variables that are in this mgtr sine 35 plus TL sine 20 equation. So I need to get rid of the mg. Okay, that's going to be 431. But the tr and TL, I got to get rid of those. So I'm going to use the summation in blue above. And I'm going to make that TL cosine equals TR sine 35. And now I can write TL in terms of TR. And if I can do that, I can put that number in the equation in red right above it. So TL, just divide both sides by cosine 20, is equal to TR cosine 35 divided by cosine 20. Crazy, right? Now in that red equation that says mg minus TR sine 35 plus TL sine 20, I'm going to substitute where I see TL, and I'm going to put this in this equation. So I'm going to write this. You can see where I substituted. So now it's mg TR sine 35 plus TR cosine 35 divided by cosine 20 times sine 20. All right, don't get all thrown off by all the trig, the cosines and the sines. Those are just numbers in your calculator. So you just put cosine 35 and it pulls that number out from a table. Cosine 20 pulls it out from a table. But here's a cool trig identity. Tangent is equal to sine over cosine. Whoa, here it is. Sine 20 degrees, cosine 20 degrees. As long as they're the same angle, it's also equal to tangent of that angle. And that'll just make our math a little bit easier. So now mg is equal to TR sine 35 plus TR cosine 35 times tangent 20. And you didn't really have to do that step, but it just makes it easier and takes less space up on the paper if you did. Okay, so where are we? Oh, the TRs. Notice there's a TR in front of sine 35 and TR in front of cosine 35 tangent 20. I'm going to use the distributive property and pull the TR out. So mg is equal to TR times the remaining stuff. You can see where I pulled the TR from in front of each one of these expressions. And now TR looks crazy. TR is equal to mg divided by sine 35 plus cosine 35 tangent 20. And that is equal to, well, the 431 divided by the numbers sine 35 plus cosine 35 tangent 20. And when I do all the math, remember when you're putting it in the denominator in your calculator, you got to put it in parentheses or else it won't get it right. But all that should equal 495 newtons. Man, right now looking at your paper, you look smart to everybody else. So now when I list my givens, for TL, I take TR and I put it back into my equations and do the calculations. And now I've got them all listed. So I'll just make them all known. TV 431, TR 495, TL 432 newtons. And this is what my paper looks like when I'm all done. Crazy, right? I've got the Freebody diagrams, the ones with the broken up components, and then it reads kind of like a newspaper column, and I have arrows to try to help me figure out the flow. This ended up being a lot bigger problem than I anticipated. So I had to use arrows, and then I put boxes around my answers that I'm looking for because it'll be a lot easier to find on the paper later.